Well, good day, everyone. I'm going to talk about concrete, which is a material that I have no doubt that with which you are already familiar. Nevertheless, there are some things that may interest you. There's some things, as I say, that you might already be well aware of, but I'm going to run through this material. Again, this is something you probably already know, but it's important, I suppose, to know what the ingredients are in concrete. It is, of course, a composite material. Now, I'll go into that a little bit more later on, but nevertheless, the prime components of the slurry of concrete are cement, ballast and water, and sand. And of course, these are natural resources of which we are using up the world's supply at a very high rate. So the industry is looking to alternatives for all of these, specifically for cement, because cement is a very high energy, uses a lot of energy in its production. Again, the most common type of cement used around the world is known as Portland cement. But what we're looking at now, in terms of substitutes, are fundamentally the things that you see in front of you. Fuel ash, you might also known as fly ash, blast furnace slag. Now that's the product of turning iron into steel, and of course that's another industry that's threatened. So how much of that is going to be available, we don't know, but there's an awful lot of it around already. Silica fume, which is again a byproduct, and limestone. Limestone, which of course is used to make substitutes in the first place, but there are parts of limestone that have been rejected, if you see what I mean, that they're now looking at re-involving again. This will again be a composite. It'll be a compound of cement and lime. It's also worth thinking about sand, because of course you think the world is just full of sand, but it's not necessarily building sand. Building sand is what's known in the trade as sharp sand. The reason it's sharp sand, it's not the sand that you see on the beach, which has been rounded by thousands of years of erosion by water and softened. We need the sharpness in the sand in order to bind with the glue, the cement, and the ballast, the stone that goes in with it, the pebbles, if you like, that go with it. So sharp sand is not the same as what you might think of, the Sahara Desert or as I say, sea sand. And of course, just to note that sea sand you certainly can't use it, especially not straight from the sea, because it's full of salt, and salt, as you're probably aware, is a great destroyer of buildings. Here's some aggregates. So how do we pour concrete? Well, again, this is something you know. It's just that the phrases might be different from according to where you are in the world. We call it formwork. You might have heard the word shuttering, which is the mold. It's important to remember that whatever you pour concrete into, when you take away that mold or shuttering, what is left is that the surface of it will imprint itself onto the concrete, or worst, will tear itself away from the concrete if there isn't. You can see there what we call a releasing agents. Often it's a simple kind of oil, something like that will stop the concrete adhering to whatever the formwork that you're pouring it into. And again, the curing process is quite interesting, because it really controls how quickly you can put buildings together with concrete, especially if you're looking at high-rise structures, because yes, concrete gains an awful lot of its strength fairly quickly, but after that the curve gets slower and slower, and it takes a long time to reach its absolute, its maximum strength. Now, the last fact, again, is something that you know very well, but I want to, excuse the pun, reinforce it. Concrete is a composite material. Like all masonry, like all high-dense materials, it is low tensile in nature. It cannot take tensile loads. Therefore, you cannot make columns, you cannot make bridges, you cannot make any kind of beam out of concrete without reinforcing it. It usually, if it's a beam in the lower part of it, because that's where the stresses are, without reinforcing it with a tensile material, traditionally steel. reinforcing bars, what the Americans call rebars. So, again, it's an obvious thing, but it's actually critical. It's a composite material. It's very similar to timber in that way. Timber has resin, which is if you like the concrete itself, and it has fibers, and the fibers do the work of the steel reinforcement in concrete. So we're mimicking what nature does very efficiently again. And if you ever needed any proof of that, some of you might be familiar with this. It's not far away from the university campus that you may or may not be in at the moment, in the Marylebone Road. This is at London Zoo. It's the Penguin Pool. It was designed by the architect Lubetkin, Lubetkin, back in the 1950s. You can see there's no penguins in there now. It used to be occupied by penguins, and it was a very cute sight, as you can possibly imagine. Lots of penguins standing on this ramp. They also had little sentry boxes that they would live in around the edge of it. It was very beautiful, and they were there for many, many years, 30 or 40 years probably. Penguins lived there until the zoologists or whoever was looking after them realised that they really weren't that happy, and they've moved them to a much more kind of natural environment, if you like, not far away from this. But it remains in the zoo as an icon, as a beautiful piece of architecture, and you can go and visit it. It was the first time when they designed these ramps, these beautiful circular ramps, that they tested them. When they load tested them, they realized that they did actually flex. They moved a little bit, of course, without cracking, and it was the first time that it really had been appreciated that concrete could go into bending without failing, under a sort of limited amount of load. So here it is in the making, and again, it's two things that are certainly pertinent from this image. One is that, as you can see, concrete is steel, or at least per mass, per volume, about the same, or near as damn it the same amount of steel goes into a reinforcing cage goes into concrete. Also, that traditionally concrete was a carpenter's trade. Casting concrete was a carpenter's trade. So this extraordinarily complex geometry that's going on here was achieved by carpenters. But this is the sort of thing that we would like to encourage you to think about this year, this process of construction. You can draw the formwork. Draw the formwork. That's what the architect's expected to do. You can't just make a model with some lovely ribbons on it or some kind of 3D printing. You've got to understand how are you going to support this concrete while it is being created. Here's another beautiful example. I'm not entirely sure this is possibly Candela, Felix Candela, working in South America. I apologize. It's a thin shell vaulted structure, as you can see, or it will be. Incredibly thin shell, and that will be another lecture when we look at how to achieve these sorts of minimum surfaces. But again, it's just proof and point that that it's the formwork in a way that you're interested in. And that's what you'll get if you get your geometry right. You'll get these fantastically beautiful enclosures. Actually, using if you do have to use concrete, how minimally can you use it? Isn't that a beautiful example? So another way of doing formwork, and this was developed by a man called Dante Bini, again in the middle of the last century, was to inflate it. It was hardly imagined possibly. How do you inflate concrete? Well, he did, and what he did was he built effectively. You can see, you start at ground level. The clever part, if you like, or the cleverest part, is that the rebars, all the reinforcing, is spring loaded. So as what's underneath here is a membrane, of course, which you pump with air. You pour the fairly dry mix of concrete onto the. You put the rebars in. You put a dry mix of concrete. You put another membrane, and then you start to inflate it. And as you pump it up, the reinforcing bars can expand because they've got springs within them. If you see what I mean. And slowly but surely, you pump up the concrete till you've achieved the state that you wish. In the end, and then you take away the covering. You take away the air. And you could cut holes in it and do all sorts of wonderful things. This was the 70s, I imagine, which is hence you've got the slightly long hair and short trousers, but there you go on the building sites. But they're very beautiful structures. So just to remind you that this process, it's not an ancient process. It's still Binney domes, or Binney shells as they're known, is still a known process, still being produced to this day. They're being touted as very good for for emergency, for quick, because you can build these things overnight. Literally, you can put up a concrete dome overnight using this kind of structure, and of course it's very efficient. You're not wasting lots of timber shuttering. You're not taking a lot of time building the timber shuttering, so it's a very energy efficient way. Soft precasting can be energy efficient because, of course, you have high control over the concrete. You're making it under factory conditions, and you can be a lot more accurate if you like. What you're looking at here is actually called tilt up. So these, which of course are determined by the size of a truck, there's only a certain size you can go to in precasting anything, or actually, I think in this case, in some cases, they're cast on the ground in situ, and then hence the word tilt up, and then propped up into position and locked together. And of course, with prefabricated structures, you can do all sorts of things like put a sandwich panel together with insulation in between, and so on and so forth, which is interesting. And you can make some very beautiful objects, of course, as well. So here's an interesting project. Talking of efficiency of structure, these architects, Ensemble Studio, were commissioned to design a villa for a client. Very nice kind of work if you can get it. Somewhere in the middle of Spain. Sorry, I can't tell you exactly where. And while they were researching the site, they came across locally, just a few miles up the road, a factory that was producing civil engineering scale prefabricated concrete members for bridges, basically. And they looked at all this and they thought, hold on a minute, could we put this together and make a villa out of it? And that's exactly what they did. Now, it's efficient in two terms. It's slightly crazy, I agree, but it's efficient, A, because it's a local supplier of the product. You haven't got very far to go, so that's efficient. Transport wise, it's efficient. And of course it's efficient because you've already got predetermined that you're not even having to ask the supplier to do any kind of bespoke production. And if you'll excuse me a minute, I'm going to just go to, where am I going to go to? There. And we'll have a little look at this. I do actually apologise for the music, and it's a great shame because there was a film on YouTube which I can't seem to access anymore, but they actually did film the whole on-site process and then speed the whole thing up. You could have actually interspersed with the architect with a beautiful little polystyrene model building the whole thing together. Unfortunately, that is no longer available, but there you go. So anyway, that's a clever little project. That's the swimming pool, cantilevering off the edge there. So now this is an interesting material. You might have heard of ferrocement.
It was actually has been ripping off the public for more than a decade.
See, I've done what I'm absolutely not allowed to do.
Simple trick that takes just a few minutes.
Ferrocement was actually patented before reinforced concrete. I think only just for something like a plant pot, possibly. So that's a concrete boat. But these are not cast or moulded in the way that concrete, as you understand it, probably is moulded. It's a laying up process. It's a little bit more like the way we now make fibre reinforced plastics, fibre reinforced polymers. You lay up, you put layers together, and you build these layers around, again, a tensile, some kind of tensile structure. And in this case, it's a tensile net, a little bit like chicken wire, really. You can see them building it here. So here's another concrete boat. There's the formwork, if you like, or the form being built up out of a wire mesh, and then the concrete itself is actually troweled, if you understand that term. It's troweled onto the wire mesh, built up in layers around either side until you've achieved the structure. So it's a lot thinner and lighter than poured reinforced concrete. I think this is a project. This is a combination of the things. This is precast panels designed. I think it's Pierluigi Nervi. I apologise to him if it's not. I apologise to whoever it was if it's not. Nice, very clever little structure, but again, ferro cement, very delicate, very thin, and isn't that a nice drawing? You know, sometimes you need to remember that you don't need a lot of lines if you're good at it to describe structural form. Now, here's a modern version of it. What we now tend to do, or what you might be familiar with already, is we don't trowel up the concrete onto a mesh. We spray it on. You might have come across this, the term shotcrete. So this is an example of it. These are acoustic shells designed by Paul Bavister, who sometimes comes and lectures at the university, which is very nice. He's an acoustic specialist. They are designed specifically for little pavilions for performance down on the south coast of England, and they're made with that exact that process. There's Paul, bless him. So there again, he's using it could be part of a hyperbolic parabola, I'm not entirely sure, but he's using the shell, the geometry itself to create the structural form. So you get a very thin shell, a little reinforcing around the edge, because that is essentially, that's an arch, if you like, and these are almost like the ribs of the arch going back down to the foundation, and of course it's built up in such a way that it seems to sit very nicely in the landscape. So here's the process of construction. So here's the kind of drawings, or if you like, the thinking that we would like you to be doing when you're designing this year. Think about, okay, that's what you've got to get to. How are you going to get to it? In this case, of spraying concrete onto a fine mesh, the key, the architect does is he sets out the key lines, which are in this case these are the key lines. The location and the organization of scaffolding has to be designed very carefully. The mesh has, all of that is the kind of the enabler of the architecture, isn't it? And then once you've got all that in place, you can come along and spray your shotcrete. You might be familiar with shotcrete mainly for making, if anyone's been privileged enough to design and make a swimming pool, that's the kind of process we tend to use for swimming pools. Here's another ferrous cement house. You might like this kind of stuff, I don't know. You may or may not. But I suppose if nothing else, it does enable you to do a lot of very delicate detailing at a small scale, continuously, that you might not be able to do pouring into a mold, where you probably can't. You almost definitely can't. So it's sort of, again, as I said, it's the way we would design with FRP, with fiber reinforced polymers. It's the same kind of way that we would design ferro cement. Now here's ferro cement being, this is not the whole building, of course, you understand, but these little pods on the top here by Toyo Ito are all ferro cement. You can probably just about see the mesh. I'm not sure if you can see the mesh in some of these images around which this wonderful roofscape was designed. Here's an interesting material, and it could be the beginning of development of something rather clever. Again, useful for all sorts of things, particularly for civil engineering, possibly for emergency situations where you need something very quickly. So what we've got here is you can see it's a fabric, but the fabric's been impregnated with cement or similar, and only once it can fall into position. Obviously it can bend and and stretch into various positions. It's called drop stitching, this, connecting the top and the bottom. Again, it's a technique that's familiar. Well, I say again, it's a technique that's familiar in the textile and pneumatics. When you're looking at air structures, these are the kind of double skin surfaces that are employed. So you can lay it into whatever shape you like. You then water it, and it becomes rigid, effectively. So very good for channeling water away, making temporary irrigation channels, or even sheds and so on and so forth. So that might be something you might be interested in, or you might think of developing. And again, another way of avoiding huge timber formworks is to pour concrete into fabric. So this is a lovely project. Again, you will, when you see under your study materials, you will see there's a PDF presentation by Structure Mode, a company called Structure Mode, and their director Jeff Morrow. They're very good at looking at, because they work all over the world and often in very poor parts of the world, and they look for clever and alternative ways of putting buildings together that can use local resources or can be energy efficient. And here's one of them. So here we are pouring concrete into, in this case I think it's actually canvas formwork, pouring concrete into canvas formwork. Of course, the byproduct of that is that you don't really get the kind of hard edges. You can avoid the hard edges, shall we say, that you might get with normal formwork, and you get these really rather lovely kind of soft, they almost look like fabric, don't they, structures that are holding the buildings together. And of course, if we're getting rid of steel, we're getting rid of cement, we're gradually refining what we do. What alternatives can we use for the fiber reinforcing of concrete? Well, of course, there are all sorts of other fibers around in the world, or long fibers. Some of them are synthetic, such as carbon and aramide, the sort of things that are developed by DuPont. There are natural fibers, jute, hemp, and so on and so forth. And so the industry again is now looking at reinforcing concrete with fibers, and this gives you the chance of a sort of delicacy, if you like, that you might not be able to achieve with steel reinforcing. Okay, this is just part of a facade, admittedly, but you wouldn't be able to achieve those kind of intricate forms, I don't think, by pouring concrete into a mold. You might just get away with it if you're using very expensive self-compacting concrete and you were Zaha, but otherwise, by the way, this facade, although it looks fairly what's the word, frivolous, it is actually designed quite cleverly to deflect, because apparently there's quite high winds on this, wherever it is on this particular facade, and it's designed particularly to deflect the wind so that the facade itself doesn't take a huge lateral load. That's fibre reinforced concrete facade. So is that, if you like that sort of thing. Here is Zaha actually. Skinning what is a very, I say, very basic structure. It's just a series of platforms held. That's obviously the lift shaft, which is she's slightly. So the concrete is not structural. I accept it. The space frame is doing the structural work, and then this is this process of panelization. Each of these are. I think this is what they call a developable surface. I think they're flat panels. I may be wrong. Not entirely sure about that. Anyway, the people who design and install and create these are a company called New Technic, NEWTECNIC, whose originator, director is Andrew Watts, and Andrew Watts he's an alumni of your university, you'll be pleased to know. He was here way back in the day when it was the Polytechnic of Central London, and Andrew does a lot of these very, very complex skins or facades now, and his book is on your reading list. It's called Modern construction envelopes, which I think you can actually download as a PDF, which is rather nice. And finally, in terms of reinforcing concrete, we have this very new high-tech material called Ductal, which again, it's not a fibre, it is actually steel again, but it's tiny, it's almost like pins, needles, if you like, needle-thin stainless steel mats and that are reinforcing these. Again, this is this is Eva Jerichner, one of Eva Jerichner's design. This is lovely in itself. This is the column that supports. You might know her work. She does love expressing structural form. But these are what we're interested in here, because each of these is a precast, prefabricated concrete stair tread, if you like, which is reinforced, as I say, with very, very delicate steel. You look up ductile concrete, and you'll see there's the process. There's the molds. Rather lovely structure. So to end this, I just want to show a few things that I might be worth reflecting on in terms of what has been built with this. I've already mentioned Nervi, and I think he's worth mentioning again because and it was in the middle of the last century that concrete really did come of age in terms of architecture and engineers thinking, instead of, if you like, mimicking what had happened in the past with this material, thinking what possibilities does it give us, and every generation hopefully will do the same with the materials that are available to them, rather than sort of saying, oh, we've got this, we can do what we did before but maybe better, but we can do something different. And Nervi certainly did that. And this is the Palazzetto del Sport in Rome, and it's a lamella dome, which means it's the kind of double helix, if you like, going in different directions. So here's the ribs that reinforce the structure. It doesn't get a lot better than that, and there they are, there it is in the making, if you like. Of course, this does hark back to the days when you needed a huge amount of timber reinforcement, I beg your pardon, in timber formwork in order to cast the shell. Nevertheless, a fantastic achievement. And this is Nervi again. It's a simple shed, if you like, or fairly simple shed. It's a warehouse structure that he designed, and he designed here a series of should we call them umbrella structures that are actually, each one is self-standing. They're not structurally reliant upon each other. And the beauty of this, the reason they can do this is for one thing, as you can possibly see, the columns which taper start off as a cruciform at ground level and morph to a circle at the point where they need to be. There's then a whole load of steel beams cantilevering off the column, so that it's it's dealing with loads in all directions. At this point here, where it needs to, it's tapering. And why connect them when you can allow natural light to drop in? So these beautiful little glass connecting pieces. Anyway, I think it's very elegant. Next time you say to your tutor, "Oh, I'm just designing a warehouse or a shed," perhaps you can say, "Yeah, but it's going to be a little bit like well, there you go. That's what can be done." And I'm not sure this is the last thing it could be, but I'm going to jump now again to a bit of a film.
Lautner loved concrete as a material. Concrete was his muse. He started using concrete in an architectural way at Silvertop. Silvertop is the first one of these shell structures built entirely of concrete. And of course there are these enormously important concrete buildings like the Elrod House. But this is his masterpiece. It's not just one of his best houses. I think it's one of the most extraordinary houses of the 20th century, really. I mean, there's nothing like this. Yeah, I think we're getting close, actually. Yeah, I can see the wall.
There's the wall.
This is it, yeah.
And the way the wall and the rock go with one another is astonishing.
Yeah, this is such a beautiful situation here. Nicholas and I were curating a major exhibition of Lautner's work for the Hammer Museum when I brought him to see Marbrisa. It was his first visit. this is where the roof kind of sweeps over the whole ramp.
And you see this great structural ring for the first time. That
we turn and we'll be seeing the roof again in a second. This is it.
Whoa.
You enter the house through this gate that was designed by Matias Gerritz, a very important Mexican artist. You cross the moat on a bridge and it moves you even closer to the ceiling, and you cannot see how enormous the ceiling is because the whole thing is foreshortened. It's tilted up towards the sky. It's not until you start moving around in this house that the house starts to expand slowly.
I felt that the best thing that could be done there was to keep the beauty of the Acapulco Bay in the sky with no interference.
It's always about being within his spaces.
It is.
And never about being outside looking at them.
He never thought of his buildings as objects in the landscape.
Right.
I mean, it's always about the space and how the architectural space connects to the landscape.
The clients in Acapulco understood the idea immediately, and they just went ahead and did it completely without any quibbling or compromising, and the builders down there loved it. In fact, the builders in Mexico are architects, so the architect builder was proud to do it. Well, here you can't even get a contractor to bid one because it's not the same as every other one, and they don't want to even bother. Under construction, the people around Acapulco thought it might become a bull ring.
This was just a perfect combination of the architect, a very educated client, really a patron of the arts who commissioned Lautner and didn't interfere further with him, and then having the craftsman to do this amazing work.
Again, Lautner said how important when he did this wherever he worked, he would look for, again, what's the local knowledge, what are people good at, what's the local materials, and of course he found that there was a great tradition in Mexico in pouring concrete and crafting concrete, and so he sensibly went with that. He's where I've seen projects in America where he's worked with shipbuilders because it's timber. Who knew better about it than those people? So there you go. Anyway, of course he did mention that why put up a balustrade here, which would be awful. That was his solution. Very nice. And this could be the last one, as Robert Maillart, because this is an example, again, going back to the minimal use of concrete. You wouldn't think, would you, that this was a concrete building? Well, it is. I know it's precast or cast in situ, I'm not entirely sure. But he described these as constant force trusses. And the reason is that they are, if you remember, if any of you recall in your undergraduate looking at bending moment diagrams, when you look at the way the truss is loaded and the way it will bend or deform in terms of the diagram, he built that. That's what he built. So this is the kind of maximum stress that the truss would take. The same with the columns, which you can see beautifully just kind of bend into to take the load. Slight cantilevering going on, and then the double cantilever back out that side again there. I know you're going to say I'm obsessed with warehouses now, but sometimes being asked to do something very simple, well, I say very simple, but a kind of fairly large span, open space structure can challenge us to very beautiful structures and very beautiful structural solutions. By the way, I should credit Will McLean. These are his photographs. He went and travelled around Europe looking at concrete. Bless him. Gee, there's the bending moment diagrams. Of course, they're flipped. There's the section drawing. I keep saying it's the last thing. This could be. Well, you never know. There might be more. But anyway, there won't be a lot more. Again, Scarpa you will have heard of. Worth mentioning, not so much because of his structural wizardry, but because of the way he made this material work with traditional buildings. And of course, that's a whole nother lecture, which I'm not going to give. But there is, just to remind you, there should be a book on your book list called On Altering Architecture by Fred Scott. And if any of you at any point this year are involved in working with existing buildings in any shape or form, it's not a huge book. I would really highly recommend buying it and having a look through it. On Altering Architecture. Here's some lovely prefabricated work by Renzo Piano, and this is about controlling how natural light enters an art gallery, using concrete in that way. And here is some structural wizardry, or structural gymnastics, shall we say, Edward Torroja, who I think it was him that actually set up in early 1950s the IASS, the International Association of Shell Structures, which continues to this day. Again, I think there should be a reference under your web references. There should be some link to the IASS, or at least to a good shell structure website. These are minimal structures. They're absolutely astonishing. They're doing an awful lot of work with a very little amount of material. And sustainability or lower, having a low embodied energy in buildings is nothing new, because engineers and architects have always looked to minimize the amount of materials they use for cost reasons, their client, to keep the cost down to their clients, and just to be efficient. You can do more with less if you work that way and if you think about things like that. Thank you very much. Good night.